לא להדליק. מחכים עוד כמה אנשים, נכון? כן.
כמה, צריך להיות איזשהו כמות מינימלית של חצים, אבל שני חצים יכולים לעשות אותי.
נכון, כן.
אז איך
אני לא יודע, אין
איזה חוק.
אני לא מכיר איזשהו חוק.
כי כאילו לכאורה צריך אינטגרל על כל זה, אבל אתה אומר, טוב, אני מספיק לקחת...
כן.
אוקיי, אין איזה...
יש עוד מישהו שצריך להיכנס? אתן נכנסות?
כן, נראה לי כאילו
באיחור? טוב. נראה לי שכן.
אני צריכה לצאת, לא יהיה
אוקיי.
היום.
יש באינטרנט, לדעתי. את תביני. טוב. אוקיי. אני פשוט אתחיל. Okay, let's start. We are dealing with the topic of chaos. And last week I introduced chaos in three-dimensional nonlinear systems. So today I'm going to present a few things about that, focusing on the Lorentz system as the classical example. And then we will move to difference equations, also called iterated maps, which are, we take one-dimensional systems there, and we will see how they also give rise to chaos. But they are interesting even if they are not chaotic. Okay, so we were talking about the Lorentz system, which is a model for convection in the atmosphere. And last time I showed you this strange attractor, the butterfly shape. But there were a few bugs, so I'd like to give the full demonstration now. So we saw that we get this aperiodic behavior. And we will talk today how we can know that it's actually aperiodic. And we also said that there is a very high sensitivity to the initial conditions. So here I will take a different condition, which is close by. If this were a system with an attractor like a fixed point or a limit cycle, equal to the x, it's arbitrary. Doesn't matter, just to pick a point, I had to set the z to something. Okay, so you see, I started from here. If this were a non-chaotic system, we would expect that these 2 points will lead us to the same place, either to a fixed point or a limit cycle or diverge to infinity, unless there's a separatrix going between them, by chance. And here we see the trajectories for these two close initial conditions, and we see that they are different. And I think this is a trajectory from the first one, and this is from the second. So you can see that it looks like they are occupying a similar set or a subset of the 3D space, but they don't repeat each other. So they are basically lying on the same strange attractor, but they don't cross each other. This is what is so strange about this attractor, because it's not actually a surface. I told you it has a dimension, a fractal dimension of just over 2. So trajectories can go a little bit above or below this surface that would approximate this butterfly shape, and then they can go on and on forever without crossing each other and without repeating one repeating itself or the other. Okay, so this was just me picking 2 points. And because they cannot generate a very, very small error or perturbation or deviation, I have here I have the code do it on its own. I pick this initial condition, and the code will give us a delta of 10 to the minus 10 from this on the x dimension. Okay, it's busy. Okay, so you see here that, can you see? This is okay. So you see that the blue and green initially kind of overlap, but at some point they start to deviate more significantly. Probably there are also deviations here that we don't see. And then things become very different. You see these peaks that are different for the 2 conditions. Yes. And now if we plot in the phase space, so you can see that they followed the same path to the strange attractor, as far as we can see here at least. But then in the strange attractor they do different things, which is the difference that we saw over there in the time plot. And last lecture, I introduced the Lyapunov exponent as a measure for the sensitivity to the initial conditions. So we said that we could plot the logarithm of the deviation against time, and the initial period will give us an approximately linear relation, or what we could imagine is some line passing here. And eventually we get to very large deviations. You see around the logarithm is around 0, and this is the scale of the strange attractors. So they can only be so far apart on the strange attractor. And this is what we see here. They oscillate within this attractor, and they get closer and farther away from each other. So this is the deviation on the x-axis. We can also plot the deviation on the y-axis and deviation on the z-axis. And here they are about the same. And basically the linear fit that we will make here will give us a slope which is the Lyapunov exponent for each dimension. And we are interested in the largest Lyapunov exponent. If one Lyapunov exponent is, say it is an order of magnitude smaller than the rest, then still the behavior of the system is chaotic. Now, the more practical meaning of this is that in chaotic systems, there is an inherent limit on predictions that we can make. Okay, so we say that there is a horizon, a time horizon, beyond which we cannot predict what happens to the system. Yeah, it's deterministic, but say that you have an initial error in the state of the system. Okay, it can be a measurement error, and that will be delta 0. We'll make it a vector. And so this error is amplified according to the exponent of lambda t. So if there is some error that we are willing to tolerate in our prediction, we'll call it A, then the time that our prediction will hold within this error, we call it t horizon. It's of the order 1 over lambda times the logarithm of A over the initial error and in any case it will be a few multiples of 1 over lambda.
But wouldn't it depend on how accurate you're willing to be or inaccurate you're willing to be?
Yeah. So say delta 0 has an absolute value of 10 to the minus 10, and say A, you're willing to be accurate up to 0.1.
A is how much, the accuracy level.
Yes, that you're tolerating in your prediction. So here you'll get 9, so it'll be 9 over lambda. Okay? In any case, lambda is setting this time, the order of the horizon time. Excuse me? This? So
How do you get 0.1?
no, this is arbitrary. I decided.
What would you calculate to get?
So I gave this because the strange attractor. Let's see. Okay, so the strange attractor, you see it's of the order of 50 units across here, minus 20 to 30. Okay, and it doesn't mean anything if my system is here and I predict it to be here, right? So I said, okay, order of 1, maybe order of 10. So it doesn't matter. Order of 10, you'll still get 11 over lambda. So of course, lambda is a time constant, and it sets the time scale of the predictions that we are able to make in chaotic systems. This is, of course, very worrisome for us as scientists or neuroscientists trying to deal with systems that may be chaotic. There is actually no good treatment for a chaotic system. We cannot predict it. But I'll show you that there are a few things that we can say about it, and sometimes we do with that. Also, some people look at what they call the edge of chaos. For example, in neural networks, they would look for the parameters that give you a transition from a negative lambda to a